Now finally, we will summarize the capacitors in parallel and capacitors in series in tabular form due to which we can easily understand the difference between the capacitors in series combination and capacitors in parallel combination. So, capacitors in series and here capacitors in parallel. First point is, in series combination of capacitors, what is same? Charge on each capacitor is same. And the value of this charge on each capacitor is equal to charge supplied by the cell. Again, what is different in series combination? Potential difference across each capacitor is different. And in this case, the total PD applied is equal to sum of potential difference across individual capacitors in series combination. In parallel combination, which quantity is constant? In parallel combination, PD across each combination is same, and which is equal to PD of source. What is different? Charge on each capacitor is different, and therefore total charge is equal to charge on individual sum of the charges on the individual capacitors. So this is the one point. The second point we have studied is the equivalent capacitance is given by 1 upon Cs equal to 1 upon C1 plus 1 upon C2 plus 1 upon dash plus 1 upon Cn. That means the reciprocal of the equivalent capacitance is equal to the sum of reciprocals of individual capacitance. And if we consider C1 which is equal to 2 microfarad, C2 equal to 6 microfarad, and C3 suppose which is equal to 12 microfarad. Then in case of series combination, the equivalent capacitance is given by 1 upon Cs equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3 for these three capacitors. So 1 upon Cs is equal to 1 upon 2 microfarad plus 1 upon 6 microfarad plus 1 upon 12 microfarad, and which is equal to 9 divided by 12, and therefore the equivalent capacitance when three capacitors are connected in series come out to be Cs is equal to 12 divided by 9, and it comes out to be 1.33 microfarad. So from this example we conclude that if capacitors are connected in series, then the equivalent capacitance is come out to be 1.33 microfarad. So conclusion is drawn that the equivalent capacitance of series combination is less than the least value of capacitor in series combination. So we have connected 3 capacitors in series, 2, 6 and 12, but the equivalent capacitance becomes 1.33 microfarad, which is less than the least value, that is 2 microfarad in series combination. And in case of parallel combination, second point, Cp is equal to C1 plus C2 plus dash 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 plus Cn. Again, if we take the same charges, 2 microfarad, 6 microfarad and 12 microfarad are connected in parallel, then the equivalent capacitance Cp is equal to 2 microfarad plus 6 microfarad plus 12 microfarad, and which comes out to be 20 microfarad. So, when capacitors are connected in parallel, the equivalent capacitance of 3 capacitors, 2 microfarad, 6 microfarad, 12 microfarad, it comes out to be 20 microfarad. Then we draw the conclusion that in parallel combination of capacitors, the equivalent capacitance is greater than the greater value of capacitance in parallel. So in this case, the largest value of 3 capacitors in parallel is 12 microfarad, and when they are connected in parallel, the value Cp come out to be 20 microfarad. So Cp is greater than the higher value of capacitance in parallel combination. Now next point is, if n identical capacitors are connected in series, then Cs is equal to the value of Cs is equal to C divided by N. Again, if n identical capacitors are connected in parallel, then we get equivalent capacitance Cp, which is equal to N into C. So when n identical capacitors are connected in series, equation is Cs is equal to C by N, and when the same n identical capacitors are connected in parallel, then expression Cp is equal to N into C. And from these two equations, we conclude that Cp upon Cs, which is equal to Cp is Nc divided by Cs is C by N. And therefore the expression for or the relation between Cp and Cs is come out to be n square, and therefore the Cp is equal to n square times Cs. So when n identical capacitors are connected in series and again these n capacitors are connected in parallel, then we have get the formula Cp is equal to n square times Cs. Now the next differentiating point we have to discuss is if again n identical plates are arranged such that 1, 2, 3, 4, 5, 6 and so on, n number of plates are arranged in this manner, then in this case the number of capacitors formed and these capacitors formed are parallel plate capacitors and their value is n minus 1, and all the capacitors are in series. So if number of n identical plates are arranged as shown in figure, then n minus 1 parallel plate capacitors are formed, and these n minus 1 parallel plate capacitors are connected in series, and therefore in this situation the equivalent resistor capacitance C is equal to C divided by n minus 1, where the C is the capacitance of parallel plate capacitor. And if we substitute the value of this capacity of parallel plate capacitor filled with dielectric, then the value of this C is A K epsilon 0 and divided by D, and in the numerator the term is n minus 1. So we have obtained the formula when number of identical plates are arranged in this manner, the number of parallel plate capacitors formed which are equal to n minus 1, and these capacitors are connected in series, then the equivalent capacitance come out to be A K epsilon 0 divided by n minus 1 in bracket outside bracket D. Similarly, we can explain about the parallel plate capacitor. If n identical capacitors, so n identical plates are arranged such that, so this is plate number 1, 2, 3, 4, 5, 6, 7, 8, 9 and so on. Now if we connect odd number of plates together, so plate number 1, 3, 5, 7 and 9 are connected together, and even number of plates are connected together, so 2, 4, 6, 8 and so on, then we get n minus 1 capacitors which are connected in parallel. So when n identical plates are taken and odd number of plates are connected together and even number of plates are connected together, then n minus 1 parallel plate capacitors are connected. And again in this case, the equivalent capacitance of the parallel combination is given by formula Cp is equal to n minus 1 into C, and which is equal to n minus 1, outside bracket the value of C is again AK epsilon 0 divided by D. So when n identical plates are taken and if odd number of plates are connected together, even number of plates are connected together, then we will get n minus 1 plates are connected in series, and in that case we have find the expression for equivalent capacitance in parallel combination. The next point we are going to study is as we know that energy is equal to 1 by 2 into Q square by C, and the expression for and in case of series combination of the capacitor, the charge on each capacitor is the same, and therefore we write energy U or energy E in capacitor is inversely proportional to C. So energy in capacitor stored is inversely proportional to C in case of series combination, because the charge on each capacitor is same. And in case of parallel combination, we know that potential difference is same for every capacitor. Again we know that expression for electric energy is equal to half CV square, but in parallel combination potential difference is the same, and therefore energy stored by the capacitor is directly proportional to the C, that is capacity of a capacitor. Again, we observe that the energy expression is U is equal to, or energy stored by the charged capacitor is given by the formula 1 by 2 CV square. So, in series combination of capacitors, we write the energy stored by the series combination, which is equal to 1 by 2 CS into V square. But again we know that the equivalent capacitance in series combination is less than the least value of capacitor in series combination. That means the value of this CS is very small and the applied potential is V. Then in case of series combination of capacitor, energy stored is less or it is least. So series combination cannot store large amount of energy. And in case of parallel combination of capacitor, again we have the expression for energy E is equal to 1 by 2 CV square. As in case of parallel combination of capacitor, we write energy expression which is equal to 1 by 2 Cp into V square. Again, in case of the parallel plate combination, the equivalent capacitance Cp is greater than the greatest value of capacitor in parallel combination, and therefore as Cp is greater, then the energy stored by the parallel combination is also greater or it is large. That means a series combination cannot store large amount of energy, but a parallel combination of capacitor can store large amount of energy. And finally we discuss one point regarding the capacitors in series and capacitors in parallel. So in case of capacitors in series, if two capacitors C1 and C2 are connected in series, then we have got the equivalent capacitance is equal to C1 into C2 divided by C1 plus C2. And in case of series combination, we know that the charge on each capacitor is same, that is Q is equal to Q1 is equal to Q2 is equal to so on. Then Q1 is C1 into V1, Q2 is written as C2 into V2. For the case of two capacitors connected in series combination, we have write a charge is same, C1 into V1 is equal to C2 into V2, and which is equal to Q, and the Q is nothing but Cs into V. So the value of this Q is Cs into V. And from this expression, we can obtain the expression for electric potential across capacitor number 1, C1. So C1 into V is equal to C2 Cs into V. So we write V1 is equal to Cs into V divided by C1. Again the value of Cs is C1 into C2, and this multiplication V divided by C1. So Cs is equal to C1 into C2 divided by C1 plus C2 and into this voltage V and divided by C1. So in this expression, this C1 and C1 gets cancels, and therefore we get the potential difference across the capacitor C1 is given by the formula V1 is equal to the another capacitor multiplied by potential difference applied divided by C1 plus C2. So by using this formula, directly we can calculate the PD across capacitor C1, and similarly we can find out the potential difference across the capacitor C2, and the value of this come out to be C1. That means the remaining capacitor out of 2 multiplied by potential difference applied divided by again C1 plus C2. So these expressions are very useful while solving the problems or while solving the numericals which are based on series and parallel combination. Again, the same can be explained in terms of capacitors in parallel. So when two capacitors C1 and C2 are connected in a parallel, then equivalent capacitance Cp is equal to C1 plus C2. And in case of parallel combination, potential difference V is same. That means V is equal to V1 is equal to V2 for two capacitors. And we write the value of V as C is equal to Q by V. This is the basic formula. So from this V is equal to Q by C. So this V is equal to Q divided by, or it is Q1 divided by C1, Q divided by Cp here, which is equal to Q1 divided by C1, which is equal to Q2 divided by C2. So in case of parallel combination, as PD is same and charge on each capacitor is different, so value of Cp come out to be Q divided by Cp, value of V1 come out to be Q1 upon C1, value of V2 come out to be Q2 upon C2. And from this expression again, we can directly found the charge on capacitor C1, which is Q1. So charge on capacitor C1, which is equal to Q1, which is given by this Q1 is equal to C1 multiplied by Q divided by Cp, and the value of Cp is C1 plus C2. So charge on first capacitor is calculated by using this formula, and similarly the charge on second capacitor Q2 is equal to C2 into Q divided by C1 plus C2. Again, in case of parallel combination, as the charge on each capacitor is different, and it can be calculated by using this formula Q1 and Q2. Again, these two formulas are very useful while calculating or while solving numericals and MCQs on these two articles.